Okay, SCH3U, let's talk about some of the more complicated ionic compounds. In particular, we're going to talk about multivalent ions, then polyatomic ions. Well, I wrote polyatomic ions. Dang. That's just not my spelling bee today. Here we go. Polyatomic ions, that's better. Polyatomic ions, then we're going to talk about going from the formula to the name, including multivalent and polyatomic ions, and then from name to formula for the same thing, for multivalent and polyatomic ions. All right, so let's talk about the multivalent ions. The multivalent ions are kind of what it sounds like, multiple valence, right? When we say multivalent, we mean many, right? Many and kind of shells, right? Kind of many shells. And so those exist primarily in the transition metals. Oh, hey, look, I made another spelling error up here. Exclusively. Let me fix that too. This is what happens when you try to type too fast, guys. Exclusively. Exclusively. There we go. Found in the transition metals. So in the transition metals, we have these metals that have a lot of electrons, and those electrons are in these kind of squiggly weird shells underneath the two main shells, underneath these shells. So they've got these weird squiggly shells, and they're kind of lumpy, and so they can lose like some electrons. They don't have to go all the way back to 0. They can lose just a few here and there. So in order to predict things in them, there are certain common things. So a lot of them will do a +2 and a lot of them will do a +1 and stuff like that, but there's no really good way to predict it. The way to actually get it is just to react them with a bunch of different things and to see what happens. Normally we do it with oxygen. And that's how we know that copper likes to do a +1 or a +2. We know that iron likes to do a +2 or a +3, and so on and so forth. So what I'm going to do is I'm going to get a periodic table that has all of those listed. And here it is. Here's a periodic table of ions. We see the normal +1, +2. These are +3, like we might expect. These are -3, -2, -1. But then there's the weirdness of the transition metals. Now these are kind of the most popular ions that these make. These can definitely make other ions, but zooming in here, you can see that copper likes to make a +1 or a +2. Nickel can do a +2 or a +3. Meanwhile, palladium can do a +2 or a +4, and platinum can do a +4 or a +2. Okay, the top one tends to be the more common one here, so that's why copper 2 is above copper 1, and palladium 2 is above palladium 4, but platinum 4 is above platinum 2, and gold 3 is above gold 1, and stuff like that. So these are multivalent ions. And it's not exclusive to the transition metals, although that's where most of them are found. If we move over here and we zoom out a little bit, you can see here, even in the non-metals, when we're down below the staircase line, things get a little bit weird down here. So tin, even though it's in that 4 zone, it can be a +4 or a +2 because of some quantum weirdness that I don't want to get into in grade 11. So literally, it's just by experiment that we know that they like to make these particular ions, and that these ions are more common, like copper 2 is more common than copper 1, or iron 3 is more common than iron 2, or manganese 2 is more common than manganese 4, and things like that. Now, these aren't the only ions that they make. Chromium, for example, can make a 6+, or I think there's a 1+ chromium as well. But yeah, there's just tables of these. You don't have to memorize them or anything like that. You'll just have a table for it. But we have to explain how to name these things so that we can transmit that information properly to other chemists. So I'm going to jump over to this, and we can show why it's important. So the reason that it's important is you can actually have different compounds. So a classic example is black iron oxide versus red iron oxide, right? Black iron oxide versus red iron oxide. And the names come from their colors. Black iron oxide is a black powder, red iron oxide is a red powder. When you do chemical tests on it, black iron oxide turns out to have 1 iron for every oxygen, and red iron oxide turns out to have 2 irons for every oxygen. How can this happen? Well, the only way that it can happen is if the iron has a different charge between the two molecules, because we know oxygen is always a 2 minus. Oxygen is always a 2 minus. So our oxide is always a 2 minus. So we can use that to figure out what the different irons are. The first one's pretty straightforward. Iron oxide. The black iron oxide, there's 1 oxygen and 1 iron. We know that the oxygen is a 2 minus. The reason that we know that is, when we do the experiments, these guys don't make any multivalencies. They just keep their -1, -2, -3 pattern going. So we know that that's a -2. That is set in stone. So what's this one going to be? Right, well, if you've been paying attention, we have to match this 2 minus, so this must be a 2 plus, which means that the iron is a 2 plus. And when we look at our formula, or at our table here, we see that iron can make a 2 plus. Iron can make a 2 plus. Right, there it is, iron 2 plus. So going back over here, that means that this is iron 2 plus. Now the other guy here, Fe2O3, the way to do that, you can write there's 2 irons and there's 3 oxygens, 1, 2, 3. We absolutely know that oxygen makes a 2 minus because there are no multivalent nonmetals. At least commonly, there aren't any multivalent nonmetals. So there's 3 of them. 3 2 minuses means that is 6 minus. And 6 minus needs to be matched with a 6 plus on this side. Okay, we have a 6 plus and there's 2 irons there. So the only way that can happen is if each iron is a 3 plus. So that's the kind of puzzle that we have to go through every time we see something with a transition metal. We have to figure out what the charge on the transition metal is. And it's pretty straightforward because we know the charge of the nonmetal. We always know what the right side is doing. We know what the charge is going to be. So we use the right side to predict the left side. And then to name it, we have to say somehow that these are 2 different things. And if you remember how we name ions, we name it positive ion and then negative ion. We keep the same naming scheme. We keep it separate by positive and negative ion. So we have to name the positive ion and name the negative ion, and then the name is the 2 of them together. This ion is an iron ion with a charge of 2, and that's how we name it, iron 2. Iron 2 is the name of this ion. It's the iron 2 ion. And this guy is oxide. So this compound is called iron 2 oxide. That is the IUPAC way of naming this ion. This ion, because it's a 3 plus, is called iron 3 oxide. Iron 3 oxide. And once again, the 2 refers to the charge on the iron. It doesn't refer to anything in the formula, right? There's no 2 in this formula anywhere. The 2 is specifically the charge on this iron. And this 3 is also specifically the charge on this iron. The 3 does not refer to saying that there's 3 oxygens, for example. That is a very, very common misconception I see, that it's iron with 3 oxygens, but it's not. The 3 refers to the 3 plus, because we named them positive ion, negative ion, and that's where you should think in your head where the name separation is, where the separation in the name is. So that's a multivalent concept. Now there's an older scheme of naming these that's based on which one is more common, and that's ferric and ferrous. So this is called ferric oxide, and this is called ferrous oxide. Actually, I'm just going to double check that because it's old and I don't remember if that's completely correct. Okay, thank you, Google. I had that wrong. This is ferrous and this is ferric. But you can see why we got rid of that. Why we got rid of that type of way of naming it, because you have to memorize what the ferrous and ferric mean. But when you just say iron 2 or iron 3, you automatically know the charge on the ion. It's really, really wonderful. So that's a polyatomic ion. There's a whole bunch of them, a bunch of different ones. Do watch out, especially down low in the nonmetals down here. Tin and antimony and lead and stuff like that. Sometimes they catch people out because they don't think that they're going to be multivalent, but they are actually multivalent ions. Okay, next thing that we want to talk about is polyatomic ions, and I'm going to pause and we'll talk about polyatomic ions. Okay, so the next piece is polyatomic ions, and polyatomic ions, if you look at them, keep in mind they tend to stay together, and we can kind of think of them as blocks of charge. What do I mean by a block? Well, think about how like oxygen 2- is an ion, and you can have like, say, iron oxide, iron 3 oxide. There's 3 of these 2- that are associated with it. Well, that would be true no matter what had that charge of 2-. So oxygen 2- is an option, but anything that has a -2 charge would have the same kind of formula, right? It'd be Fe2 something 3. Fe2 something 3. And as it just so happens, there are certain collections of non-metals that have a tendency to stay together and to be blocks. One of those is sulfate, SO4 2-. That's a block of an S and 4 oxygens, of sulfur and 4 oxygens, but together they have this charge of 2-, and they like to stay together like that. So instead of those oxygens we had before, it could just be SO4, right? And you'll have the same kind of thing. SO4. So SO4, 3. So that block, there's 3 of these blocks of SO4 now. 3 of these blocks. And that's called a polyatomic ion, right? SO4 2-, it's a polyatomic. When you break it down, that's many atoms, a polyatomic, many atoms, ion, and the ion is the charge. So it's many atoms that tend to stay together and they keep this charge. I like to think of them as blocks. When you write the formula, we have to do a little bit of a funky thing because we have to show that there are 3 blocks of SO4, there are 3 blocks of sulfate. So this formula looks like this. We use brackets, just like we use brackets in math when we want to collect terms. We collect the SO4 inside a bracket, and then the bracket tells us that that SO4 is a block. So there are 3 blocks of SO4. So this formula actually has 12 oxygens in it and 3 sulfurs, because the 3 is modifying the entire block of SO4. So that's how we deal with polyatomic ions. If we jump over to our periodic table we were looking at earlier, here is a table of various polyatomic ions for you. Here's a table of polyatomic ions. There's a bunch of them. They have names that end in ate or ite, and some other things, but usually ate and ite. There are a few exceptions. One notable exception is this guy, hydroxide. It's the only polyatomic ion that has an "ide" ending. So the last video I talked about how an "ide" ending is individual atoms that are charged, individual ions. This is the only exception. Hydroxide is specifically OH-, hydroxide. It's kind of in the name. Often the names tell you a little bit about what's in there. So for example, chlorite obviously has chlorine in it. Bromate obviously has bromine in it. Borate obviously has boron in it, and so on. Sometimes they don't really match up, like acetate is not does not match what it what's in here, because just carbons and hydrogens and carbons and oxygens, but that's not that important. So I'm going to jump back over here, and this is a lot of different ones, but I'm going to give you the ones that are very common and the ones that I expect you to kind of remember. So we're going to erase this stuff. So I'm going to get my eraser, a little cloth here. These are the polyatomic ions that I consider important and the ones that we see a lot in compounds. We're going to go in order of charge, so in order of lowest charge to highest charge. The first one, probably the most important polyatomic ion, is hydroxide. Hydroxide, it's an OH minus, so it's a block of OH. It's an oxygen and a hydrogen in a block, and there's a minus on it. Then another one that's important is nitrate. You've probably heard of nitrate. Nitrate, that's the nitrate ion. Very related to nitrate is, it's got the same charge but one less oxygen. We call it nitrite. Nitrite. So they're all charge of -1. Another one is HCO3, which actually has two different names. The official name, the IUPAC name, the one that IUPAC wants everyone to use for it, is hydrogen carbonate. Hydrogen carbonate. But the old name for it is still very much in use because it's easy to say. It's bicarbonate. Bicarbonate. Hydrogen carbonate or bicarbonate. In my periodic table here, it's called hydrogen carbonate, HCO3 minus. Those are the common ones that have a charge of -1. There's a few other ones like cyanide. You've probably heard of cyanide. It's actually a polyatomic ion. It's carbon and nitrogen. And chlorate is another very popular one. So you know what? I'm going to put the chlorate in there. Let's add chlorate. Chlorate. ClO3. Chlorate. Chlorate is another one that's common. This is kind of related to the chemical, the active ingredient in bleach. It's actually hypochlorite, but it's similar. So chlorate. Then we're going to move on to the ones that have a charge of 2, a charge of 2 plus. So the ones that have a charge of 2 plus, there is CO3, or sorry, 2 minus. 2 minus. This is called carbonate. Carbonate. Now you can see why this is called hydrogen carbonate, because it's just carbonate with an extra hydrogen. It's also why it's got a charge of -1 instead of 2 minus 2, because that hydrogen comes in as a positive charge, so it takes away one of the negatives. So carbonate and sulfate, SO4, 2 minus, have charges of -2, carbonate and sulfate. Note that every 8 so far, chlorate, carbonate, nitrate, and bicarbonate, all have had 3 oxygens, but that's not a hard and fast rule. Sulfate has 4 oxygens. And there are other ones that have 4 oxygens, or even 2 oxygens, sometimes in the 8 form. I'm not sure if there's any 8s with 2 oxygens. I think it's only 3 or 4 for an 8 ion. So carbonate and sulfate are the ones that have a charge of 2 minus that I want you to know. There's also sulfite. So given the nitrate and nitrite, what do you think sulfite would look like? There's an open question for you guys. Sulfite. Looking at nitrate. Nitrate is the same thing as nitrate with 1 less oxygen, and it has the same charge. The same thing for sulfite. SO3, 2 minus. It's that's sulfite. And then there's one of them that has a charge of 3 minus that is very common, and that is phosphate. Phosphate. You might have heard of this stuff in terms of fertilizer. Phosphate is one of the big components of fertilizer. and it is PO4, 4 oxygens, 3 minus, PO4, 3 minus. So those are the ones that I want you to know in terms of the negative polyatomic ions. And then there are two that are positive. So these are the negative ones in order of charge. And there are two positive ones. The two positive ones are NH4, which when it's in a block has a charge of +1, and H3O, which is in a block, also has a charge of +1. So this one is called ammonium. Oh, you might have heard of ammonia. This is ammonium. So AMMONIUM. It's also a great one to write if you know cursive. You can write it in cursive and it just looks like a squiggle. And this one is called hydronium. There's kind of a similar naming scheme there, hydronium. That's kind of getting awkward, hydronium. There we go. So those are the polyatomic ions. Remember, what you have to remember is that they act as blocks of charge. So they tend to stay together in reactions. They tend to stay together as an ion when they're dissolved in water and stuff like that. So we're going to go to our next topic, which is taking a formula for something that involves polyatomics or multivalence and turning it into a name. And I'm going to pause and get that set up. Okay, so we're going to talk about going from the formula to the name for various ionic compounds. Just as the keep in mind here is that all of these ionic compounds that we're going to be talking about only have two parts. So there's always going to be a positive and a negative ion, and there's various amounts of positive and negative. But there's always just two parts. So often the first thing that we do is we look at which two parts we are interested in. Well, we split it into the two parts, and then we can use that to get the name. So let's start with something simple. Let's start with something like Na2SO4. Right? This has more than two atoms in it. So the first thing we have to do is figure out where we're going to split it. Is it going to be here or here? Right? There's two places we could possibly split it. We could split it there, or we could split it there. We could split it into Na and SO4. We could split it into NaS and O4. Well, one of the hints there is that there's very few positive polyatomic ions. There's only two that we've learned is ammonia or ammonium, which is NH4 plus, and hydronium, which is H3O plus. So we're going to split it there. Now this side is obviously sodium. And when we look here on the table, sodium is not a transition metal, so we're safe. We don't need to worry about that side. Now on this side, we just have to look up in our table of ions what that's called, or we just remember it. This is called sulfate. So this thing would be called sodium sulfate. That is the name of that compound. Let's try something else. Let's try ALNO33. ALNO33. We've got to, so again, first thing first, we have to figure out where we're going to split it. There's always two parts. Well, this is pretty obvious. It's already got the bracket. The bracket tells us that that's going to stay together, so we split it there. And so we call this aluminum or aluminium, depending. IUPAC actually says both are fine. Aluminum nitrate. Aluminum nitrate. So that is the name of that compound. We can do a quick double check to make sure that aluminum is not a transition metal. It's not, so that is fine. Okay, let's get into some slightly harder ones. Let's do TiO2. TiO2. This is a transition metal. Obviously, we're going to split it there, but it's a transition metal because it's here in the transition metal block. There's titanium. So we got to watch out for what charge this is going to have. To figure out what charge it's going to have, we can do our little diagram. There's a titanium, there's two oxygens, because the 2, right, there's the 2. Each oxygen has a 2 minus. Naturally, that means that the titanium has a 4 plus. So that 4 plus gives us the charge. We know that the charge on this thing is going to be 4. So we name it titanium 4 oxide. And that's the name of this thing. It's sometimes helpful to jump back to your table and check that that's actually an appropriate ion, and yes, it is. Titanium 4 is totally an appropriate ion. Yeah. Let's try a few more. Let's do something like Ca. No, not Ca. Let's try SN. SN3 CO3. Oh no, not CO3. SN3 PO4 2. Right, SN3 PO4 2. This is kind of the hardest it can get in terms of naming one of these guys. Actually, there's one more that I can talk about to be difficult. You would have to split it here because obviously that's staying as a block because it's in its brackets, right? That's a block of charge. And as always, we can then split it up into our negatives. Right? There's 2 of these. We know from our table when we look at PO4, when we look at phosphate, and we look at our table, phosphate is over here. Phosphate PO4 3 minus. So we can look at this is a 3 minus. We've got 3 tins to match our 3 minuses. So SN, there's 3 of them. That's what that 3 is for. So SN, SN, SN. This total is 6 minus. That means this total must be 6 plus. That 6 plus has to distribute between our 3 tins. So that's going to be 2 plus, 2 plus, and 2 plus. Each tin is a 2 plus. That means that that 2 plus is the tin ion that we are going to name our compound after. So this then is tin 2 phosphate. Tin 2 phosphate is the name of this ion. So one more, and then we'll talk about doing it the other way, going from the name to the formula. So the last one here is kind of as hard as it can possibly get. I wonder what happens if I take that away. Oh, that's actually better. The last one that I'm going to do here is kind of as hard as these things can possibly get, which would be NH4 2CO3. Okay, this is weird looking, and you have to figure out where to chop it. You chop it here because that's ammonium. We have a name for that already. It's called ammonium, and this is carbonate. We have a name for that too. And that just comes from experience. When you do a lot of practice problems like this, you just learn that that's carbonate, that's ammonium, that's sulfate, that's sulfite, that's nitrate, and things like that. So that's going from the formula to the name for various ionic compounds, including polyatomic and multivalent ions. Yeah. So keep in mind this little splitting it, that they're all binary. That's a good thing to keep in mind. I'm going to pause, and we're going to do our last thing, and our last thing is going to be going from the name to the formula. Yeah, so going the other way from the name to the formula is often the hardest part of ionic compounds. So I'm just going to put up a bunch of names, and we're going to turn them into formulas. The first name I have for you is sodium sulfate. Sodium sulfate. sodium sulfate. If you look at the keep in mind up here, the negative charges are unique. So typically, it's best to start with the negative charges. And because the names are binary, we can split it into the positive side and the negative side and then bring it together at the end. So this is a good way to go. So sulfate, we just have to look at our table. We find sulfate here, SO4 2 minus, SO4 2 minus, that's a sulfate. Sodium, we have to predict the ion, so we look at our table. Here's sodium over here. Group 1, charge of 1 plus, Na plus. And now we have to match up our charges to make sure that the ions are correct. So there's 2 minus here, we want 2 plus over here, Na plus. So there's 2 Na plus and there's 1 sulfate. And then we write the formula to reflect how many of each we have. There's 2 of these, so it's Na2. And there's only 1 of these, so it's just SO4. Na2, SO4. That is the formula for sodium sulfate. Okay. Let's try a different one. Let's do calcium nitrate. Actually, not nitrate, nitrite. Calcium nitrite. And again, the same hint applies. The negatives are always known, so we can start with that negative, nitrite. It's NO2 minus. We can just find that in our table, but I have it memorized. You know, in our table here, we look for nitrite, nitrite, there it is, nitrite, there it is, NO2 minus, and we write that. Remember that it's a block, NO2 minus. Then we look at calcium. Calcium in our normal table is here in group 2, charge of plus 2. So calcium, 2 plus. Now we have to match our charge on calcium. We have to match this 2 plus. And the only way we do that is to bring in a second nitrite, NO2 minus, like that. And now we have 1 calcium and 2 nitrites. We have to write the formula to reflect this. We write 1 calcium, and then there's 2 of these blocks of nitrite. So we have to open up a bracket, put in the nitrite, and there's 2 of them. So that is the formula, calcium nitrite, CaNO2, 2. And the 2 affects both of these, which tells us that there's 4 oxygens and 2 nitrogens in our formula. That's calcium nitrite. Let's kick it up a notch with something in the transition metal group. Let's do some zinc 2 chloride. Zinc 2 chloride. And the big question here is, where do I put my split? Right? And the split goes here. Right? The negative stands alone. The negative always stands alone. The negatives are unique, always unique. So we can start with them. Cl minus. But what does zinc 2 mean? Right? So often I see students go, oh, zinc 2, that's that. But it's not. That is not what it is. Right? That's not zinc 2. Zinc 2 means that the zinc has a charge of 2 plus. Zinc with a charge of 2 plus. And then we proceed with the same thing, the same logic of I have this many charges on this side, this many charges on this side. I have 2 plus on this side, I have a minus on this side. To reconcile this, all I can do is play with the numbers. I need a second chlorine, Cl minus on the other side. And so together, when we put them together, this is ZnCl2 because there's 2 of these chlorines, and that's reflected in our formula. So that's one with a multivalent ion. You can see that it actually makes it really easy because we know exactly the charge on the zinc. Yeah. Let's try one with a multivalent ion and a polyatomic ion together. So we're going to do something like, how about lead 2 nitrate? Lead 2, no, not nitrate, phosphate. Right, lead 2 phosphate. Same concept, right? Negatives are unique. So we can split it so that the negative is unique. We know that lead 2 has a charge of 2 plus. That's what the 2 means, right? Charge of 2 plus. Lead has the symbol Pb from the Latin plumbum. It's actually where the word plumber comes from because they worked with a lot of lead in the past. And then we have to figure out what phosphate is. Of course, I know it in my head, but we'll go back to our table here. Phosphate, PO4, 3 minus. So we can write that out, PO4, 3 minus, PO4, 3 minus. And it's a block of PO4, and it has a charge of 3 minus. And now we have to play with our charges to make sure that our charges work. So you can do the crisscross method if you want, right? Crisscross method if you want. Crisscross method suggests that this thing is going to be PB3, because that's the 3 there, PB3, and then in brackets PO4, 2. But you can also do it with the visual method, where you just write out how many PBs and how many PO4s. Right now I have a 2 plus here and a 3 minus here. I need an extra PB at the very least. I've put a second one here. Now I have a 4 plus here and a 3 minus here, so I need another PO4, because all I have available to me are PBs and PO4s. Now I have 6 on this side, but only 4 on this side. Like 6 minus here, 4 plus here. So we're going to go one more PB, 2 plus, and so now I have 3 PBs and 2 PO4s, and there's my 3 PBs and my 2 PO4s. So that is taking ionic compounds from the name to the formula, from the formula to the name, and so on and so forth. I'm going to have this in EDSB for you guys to reference. It's a really handy chart. It doesn't have all of the multivalencies, but it does have a lot of them. So, you know, for example, chromium can do a +6. Various other ones of these can do other interesting ones. You know, some of them are really crazy. Technetium with the 7+7, rhenium with a +7, tungsten with a 6+. But yeah, that's ionic compounds. That's the end of ionic compounds. Tomorrow we're going to talk about covalent compounds, and that's where we get to draw the fun little structures and stuff like that. So I'm going to stop it there. Thank you very much, and I will see you guys in class.